Okay, we're recording, so let's welcome Tanmayee Gupte. She's a student at Rochester Institute of Technology. She works on the molecular relativity. Those of you who do not know yet, Rochester Institute of Technology was actually one of the first three groups who solved the numerical relativistic problem of a binary black hole merger. There were three groups in 2005, and it was a huge leap forward in the field of gravitational waves and binary black hole simulations. Now they've also started doing other things, including binary neutron star mergers. And Tanmayee is in this group that works on numerical relativity. She's a PhD candidate, hopefully will finish this year. And she'll talk to us about initial data for these simulations of binary neutron star mergers. Go ahead, Tanmayee.
Oh, hi. Good evening, everyone. So like Ofek said, my name is Tanmayee Gupte, and I'm going to be talking about initial data for binary neutron star mergers. So to give you a brief outline of my presentation, I'll give you an introduction on gravitational waves and neutron stars. Then I'll go over the background of binary neutron star mergers and the new era of multi-messenger astronomy. Like once we detected the BNS merger in 2017, it opened a window of doing astronomy in a new way, which we call as multi-messenger astronomy, because it had gravitational waves and electromagnetic waves observations in both these regimes. So I'll give you a background on multi-messenger astronomy as well. Then I'll talk about what is initial data for BNS mergers and why is it really important for studying these mergers or even making dynamical simulations. Then I'll give you an introduction to LORENE. So LORENE is the initial data code that we use. It's made up of C++ classes and all what equations does LORENE solves and what kind of modifications we had to do to LORENE in order to be able to build configurations where the total mass of the binaries was high and also the mass ratios of the neutron stars was more than one. Then I'll talk about the equation of state and what is equation of state and what is its importance and what different kinds of equation of states can we are incorporated in LORENE to calculate the initial data configuration. And in my last part, I'll talk about the dynamical simulations that we did using initial data that we produced. And that's when I'll be showing you some really cool movies. So this is the outline of my talk. Uh, so to give you an introduction of gravitational waves, so they are ripples in space-times which are caused by massive accelerating objects and some of the most violent and energetic processes in the universe. Albert Einstein predicted the existence of gravitational waves in 1916 using his general theory of relativity. So Einstein's mathematics showed that massive accelerating objects would disrupt space-time in such a way that the waves of the undulating space-time would propagate in all the directions away from the source. And these cosmic ripples would travel at the speed of light. Uh, they would be carrying information about the sources and also would tell us about the nature of gravity itself. So some of the sources for gravitational waves are compact binaries, which consist of black holes and neutron stars and combination of them. Like you have binary black holes, binary neutron star, or black hole neutron star combination. Then you have spinning neutron star, which is a single isolated neutron star that has some sort of perturbation. Then supernovae and primordial gravitational waves, which are caused by inflation. So the detectors that we have are, for example, the ground-based detectors consist of interferometers like the US-based LIGO and European Virgo. And in future, we'll be having more space-based antenna detectors, such as LISA. So we can start studying. So the way gravitational waves are studied is you make an assumption that the space-time has some sort of perturbation. For example, you define the space-time with Minkowski space-time plus some sort of perturbation, which is given by h mu nu. And so using the approximation, the Einstein equations can be reduced to a vacuum wave equation for the metric perturbation h mu nu. And so if you draw parallels between this and electromagnetic waves, the picture becomes more clearer. Like, for example, if you want to solve a wave equation in electromagnetic waves, you have to integrate over the source term. In electromagnetic waves radiation, it would be the current density. So integrate over the current density to get the vector potential. Similarly, in GR, you integrate over the stress energy tensor given by T mu nu to get the wave tensor. And if you assume the weak field limit, it reduces to the famous quadrupole formula, which is given in terms of the quadrupole moment tensor. Now I know this looks really complicated, but what we can get out of this, what is the conclusion that you can get out of the quadrupole formula is that gravitational waves, they carry energy and angular momentum from the binary system, and because of which the distance between the objects decreases and they in spiral towards each other and eventually merge. So the rate at which the binaries lose energy is given by this second equation on this slide. So because it loses energy and angular momentum, the eccentricity and the semi-major axis also reduces, and this is the reason why they eventually spiral towards each other and merge. So now to give you a brief introduction for neutron stars. So neutron stars are born from the collapse of a massive star at the end of its main sequence massive star, at the end of its life cycle, and when the gravitational force cannot be sustained by internal pressure due to thermonuclear reactions. So the nuclei in the heated core, what it does is it absorbs the electrons and turns the protons into neutrons with the help of the reaction given over here. So basically, neutron star is a star which is made up of neutrons, and if you compare the quantities to sun, you can see that they are extremely dense and really hot stars, and they weigh like a lot compared to the sun. Like I think if you take like a spoonful of neutron star, it weighs as much as the Earth. To give you an analogy of how dense neutron stars are. And originally the stars needs to be of 8 to 10 solar masses for it to end up being a neutron star. So what are binary neutron star mergers? So when the neutron stars are widely separated, they orbit relatively slowly around each other, and they emit weak gravitational waves. And like I showed you in the previous slides, that because of the quadrupole formula, they emit energy and angular momentum, and they keep coming closer towards each other. So you can see in this cartoon that the inspiral phase is the one where they are fairly apart from each other, and you can describe it using the post-Newtonian approximation up to 3 pn terms. So you don't need numerical relativity calculations for predicting the inspiral phase of the gravitational wave from BNS mergers. And so till which part of the gravitational wave can you call it to be an inspiral phase? That is where the gravitational radiation time scale is comparable to the dynamic time scale. So in the merger phase, so the merger phase starts when the distance between the neutron stars is some like multiple order, I wouldn't say multiple time, so not multiple order, sorry, multiple times the radius of the neutron star. So if you consider that the radius of the neutron star is like 10 kilometers, then merger phase would start somewhere around if the distance between them is like 50 kilometers. So in the merger phase, the binary separation is no more than a few times the radius of the neutron star, and the binary is rapidly becoming unstable because of tidal effects start taking place, and the stars plunge towards each other following onset of the dynamical instability. And so numerical relativity was very important for building the waveform during the merger phase, because we could not approximate it using any approximations like the PN approximation. So you can see in the plot that of the gravitational wave versus signal versus time that uh, the frequency keep increases as it approaches the merger, and also the amplitude. But then eventually, after it merges, it goes into the ring down phase, and during the ring down phase, it emits gravitational waves, which would depend on what kind of remnant is there. Like, what is the result of the gravitational wave merger? Is it a black hole or a neutron star? So to I'll, I'll talk about the binary neutron star merger remnant. So it always results into a compact object that is a black hole or a neutron star. So it can promptly collapse into a black hole, like as soon as it merges it will collapse into a black hole, and or it could be a short-lived neutron star, in which case the end result is a neutron star which eventually collapses into a black hole. But if it's a neutron star, if the remnant is a neutron star, there are three different kinds of neutron stars that we get of a BNS merger. The first one is supramassive neutron star, where the mass of the neutron star is above the maximum stable stationary isolated mass, which is given by the TOV equation. But this kind of neutron star is comparatively stable because of uniform rotation that can support it for much longer time because of centripetal effects. Now, if the remnant has a mass above the supramassive limit, it will fall in the hypermassive regime, where it is supported against gravitational collapse by rapid differential rotation. This does not last anywhere near as long because of dissipative forces, which will damp away the differential rotation. And the third kind of neutron star is a stable neutron star, where the neutron star mass is less than the maximum mass supported by the nuclear matter equation of state for an isolated non-rotating configuration. So these results depend on what is the initial configuration of the binaries, and also on the equation of state.
Tanmayee, a student asked me how long short or prompt collapse was, and how short were these supermassive or hypermassive neutron stars surviving for before collapse?
So the short collapse, so the promptly collapse would be, I'll show you in the movie, actually it's more clear in the movie, is you don't see a neutron star at the end of it. It merges and it promptly collapses into a black hole. And for hypermassive, I think it's order of few microseconds that it stays as a hypermassive neutron star and then eventually collapses into a black hole. Supramassive, I'm not very sure, it might be few seconds, but I know hypermassive is for a few microseconds. Should I go forward? Should I go ahead?
Yes, thank you. Go ahead.
Oh, okay. So the first, to give you a background about the multi-messenger astronomy, the first BNS merger was detected by LIGO and Virgo in August 27, which is called the GW 17087. And why was this such a huge, it was a huge discovery at that time when people were celebrating all over the world, was because uh, the gravitational waves were accompanied by signals from radio frequencies to gamma rays. So the entire electromagnetic spectrum was covered. And this was the first time that gravitational and electromagnetic observation from a single source was detected, and it started this new era of multi-messenger astronomy. And so BNS mergers, they provide the best joint gravitational wave and electromagnetic sources for multi-messenger astrophysics. And because of this, it has potential for looking at challenges which we weren't able to do before, such as the nuclear matter equation of state. So how does nuclear matter behave in extremely high conditions, for example? And binary black holes, on the other hand, do not emit any kind of electromagnetic waves after they merge, which is why BNS are so much more interesting, at least for me, I mean. And so since BNS mergers, they tear apart their neutron stars. Like, for example, if you have um, a massive neutron star and not so massive neutron star, the massive neutron star will tear apart the smaller neutron star. And because of which, it will give us a window into the interiors, which are unavailable through the other techniques. And also the gravitational wave signals from post merger, they are likely to occur at frequencies which are higher, too high for LIGO to be sensitive towards, and therefore EM observations are important because we get a lot of electromagnetic observations after the merger happens, like we saw it for GW 170817. So GW, it was the first signal that was detected, and why it was really interesting is because it was made by LIGO Virgo and also 70 other ground and space-based observatories all over the world. Um, and with the help of with the help of Virgo, so LIGO, both the LIGOs were able to detect the signal, and because even Virgo was able to detect it, they were scientists were able to use triangulation to locate the event to an extremely high degree in the sky. And with the help of EM observations, we got it to a really high precision of where the event was happening. And the chirp signal, it lasted for around 100 seconds, which is extremely long compared to binary black hole merger signals. So why is initial data important for PNS mergers? Now, uh, PNS mergers, they have a rich and interesting phenomenology as compared to binary black holes, because matter is present and you have to consider fluid equations in your general relativistic calculations. So the recent gravitational wave detection of GW 170817, it led to a particularly interesting challenge of constraining the equation of state of nuclear matter inside neutron star, which was still theoretically unknown to us. And the equation of state, it describes the dependence of pressure to density and various other parameters, and it will leave imprints on the BNS merger process and also the emitted gravitational wave signal. So BNS mergers can be used as an astrophysical lab to investigate properties of nuclear matter in extreme conditions in a way which was largely inaccessible to other observational techniques. For example, so for source parameter estimation, we need to compare the observed signals to theoretical gravitational wave templates, which depend on different characteristics like the total binary mass ratio, and the EOS. So, for example, the gravitational wave, it will depend on different parameters, and you need to build a bank of templates um, using dynamical simulations. And those the gravitational wave will depend on different parameters like binary mass ratio, and EOS. So you need to give different kinds of these three values of binary mass ratio, and EOS to cover the whole parameter space of the gravitational wave uh, for covering the whole BNS merger. Um, so numerical simulations, they are required to predict the gravitational wave from early in spiral to post-merger phase. And we can also predict the final stage of the merger, that is the merger remnant, which is also very interesting because for GW 170817, we were not able to clearly state what it was at the time when the merge event happened, but they're still processing the data in order to find out what the remnant could be. So the initial data code that we have used is LORENE, which is Langage Objet pour la Relativité Numérique is the full form, and it is publicly available multi-domain spectral methods code, which can solve elliptical equations and generate quasi-equilibrium binary configurations in GR. So what it does, it uses general relativity and the TOV equations to model isolated neutron star, which is the first step. And we begin a relaxation by superimposing two TOV solutions on each other. And it assumes quasi-equilibrium configuration, which means that it is a rotational binary, that is, it assumes rigid flow. It has spatial 3 metric, which describes the geometric structure of the space-time, and slow circular in spiral. So LORENE solves nonlinear elliptical equations using spectral methods and mesh refinement techniques. It allows the placement of quasi-equilibrium ellipsoidal surfaces at the boundary of the neutron star. And this is critical for generating good initial data because it will minimize Gibbs errors. So for example, it does that by using domain method in which so the domain boundaries, they fill all of these space and they're centered around each of the neutron stars. So for example, the upper diagram, it shows the domains which are set by LORENE. And in the below figure, you can see the green lines. Those are the domain boundaries and they are centered around each of the stars. And because of which, so one of the domain also covers the surface of the neutron star, and this helps in reducing, and because the domains are circular, you can model the neutron star, and which helps in reducing which helps in minimizing Gibbs errors. The code splits all fields into components centered on each star, so this minimizes errors from the stellar surfaces, but it does not eliminate them. And so each field is calculated in a split fashion, and the domains fill off all the space. So what LORENE does, it uses the conformal thin sandwich formalism to generate quasi-equilibrium NS-NS data, where the conformal 3 metric is spatially flat. And it specifies a helical killing vector as the configuration advances forward in time. And all the quantities, they remain unchanged when properly rotated at constant angular velocity in the azimuthal direction. So it assumes maximal slicing of the hypersurfaces, and what LORENE does, it solves for the 5 elliptical equations for the lapse, the shift vector, and the conformal factor, which is the numerical relativity part. And this is done by the 3+1. So what you do is you split the space time into 3+1 configurations. That is, you assume you split the space time into time slices. Like you have the 3-dimensional space where the time is suppose t is equal to 1. Then in the next one, you have again the 3-dimensional space where t is equal to 2. So this is called as a 3+1 formalism, which they use to split the space time into space and time, and they use this formalism for uh, solving the 5 elliptical equations, which make it conveniently, it's a lot of process, but it makes it easier to solve them computationally, which is why they go through this so much effort of splitting up the space. And you can see that there are only 3 equations, but the shift vector, the beta I, has 3 different components. So that's why it comes out to be 5. And the ki is the external curvature. Okay, so when we started working on this project, it was it had multiple failure modes. Lorene had multiple failure modes because it has a complicated relaxation scheme which uses 6 different relaxation parameters for different field components, and the safest choices that we were able to build configuration for were binary neutron stars, which were well separated but not too separated, because as we saw in the picture of the domain boundaries, that as you go away from the center of the star, the resolution becomes coarser. So the farther you are from the center of the star, the resolution is coarsest in the outermost domain. So that's why you cannot have configurations that are too separated. And the current routine that we use to locate the rotation axis, it relies on an unstable secant method implementation, um, where the numerical fixes for the equation whose zero we want to find out were necessary. So before we fix the routine, you can see that in the diagrams, like it had unsteady behavior of the position of one of the stars, or the center of mass would oscillate a lot, like wander around a lot before it would settle down. And this has been historically been a barrier for generating mass ratios far from unity. So the secant method, which is used to find the zero of a complicated function, but in this case it would be the one that specifies the location of the position of the rotational axis, and the functional choice of each star require a division by a term that could possibly go to zero, leading to non-continuous behavior of the function, whose root the routine was attempting to find out. So what we did to fix it was we took the reciprocal. Like for example, if you have 1 over f1 minus 1 over f2 is equal to 0, and f1 and f2 had a potential of going to 0, so we just flipped them, like we did f2 minus f1 is equal to 0. And using this fix, we are able to produce initial data which are far from unity without any hassle. So the second problem that we encountered with Lorene was it was not able to produce high mass binaries, like where the masses of the neutron stars was really high. So Lorene's relaxation scheme, it makes it extremely difficult to relax configurations extremely slowly. Like different effects, they come in at different time step because certain quantities are recomputed from scratch. And it is best to assume things will end up underdamped. So we build a Lorentz stepping routine where the most stable results, they begin from low mass configuration and they move inwards to the desired radius and then slowly increase the target mass of the binary. So for example, if you look at the diagram, it shows the Lorentz stepping routine that we used. So the configuration, it will start like at higher separation distance, and it will relax to 45. Like if it starts at 50 kilometers, it will relax to 45 kilometers and then slowly increase the mass. But if you want a configuration at 40 again, you need to again start at low mass separation, at low mass binaries at separation 40 kilometers and then increase the masses. Using this stepping routine, we were able to produce high mass binaries, initial data for high mass binaries. So equation of state. So the LORENE can deal with three different kinds of equation of states. The polytropic EOS, where pressure is a simple function of density, K rho to the power gamma, where gamma is the adiabatic index. Or the second equation of state is the piecewise polytropic EOS, where you kind of stitch the equation of state using four segments of polytropes, like shown in the figure on the slide. And the piecewise polytrope, it is parameterized using the adiabatic indexes, that is gamma 1, 2, and 3, and the pressure at the first dividing density, which is shown over here by P1. So the low density region is not typically resolved, but high density behavior, it can be captured using the parameters. So you assume that it has a fixed crust, and then for high density, you can model it using the parameters. The third kind equation of state that we are currently working on to build the initial data is called the tabulated equation of state, which assumes the liquid drop model with Skyrim interaction. So you can get the table at this website. So why is it called tabulated EOS? Is because it basically consists of tables of how the pressure and density varies at different points in the neutron star. So that's the third equation of state that we are currently dealing with. So why is it important uh, to study the equation of state for these binary neutron star mergers? So now the current candidates for the equation of state models for which the neutron star cores are dominated, they depend on what kind of particles are in you're assuming them to have. Like for example, by nucleons, hyperons, pion or kaon condensates, and by strange quark matter. So these are the different kinds of candidate EOS that we are considering. So for example, if you see in the left diagram, you, depending on what the gamma 1, 2 and p values are, you can think of you can see that the nuclear matter consists of different particles. um, so there are 34 different sets of EOS, and also it depends so the mass versus radius relation also changes from a different, if we assume different equation of state, which can be shown on the diagram on the right. So for different USs, the mass and radius changes differently, uh, which is really the reason why we need to study the EOS for nuclear matter, so that we can learn more about what kind of particles are made up of the neutron, what kind of particles are there in the neutron star cores. Um, so we have compiled an initial data library which consists of the piecewise polytropic EOS, and it is a publicly available library which anyone can access, and given at this website. But the data, it can be used as an input for Einstein toolkit to run a dynamical simulation. So the equation, we have compiled 7 different EOSs, and the masses are, they go from as high as 3.4 total solar mass. So you have configuration of 2 plus 1.4 and till 1.4 plus 1.4, which is like the equal mass configuration. So dynamical simulation. So one of the ways by which we can prove that the initial data that we have built using LORENE, if it makes sense or not, is by making it go through Einstein toolkit and perform dynamical simulations and see that the physics that you see during the simulation makes sense or not. So we have done, because these simulations take like weeks to happen, and then you have to process it and make a movie out of it. I can show you 2 different movies for 2 different EOSs, and which have, in the first case it is equal mass, and in the second one we have a higher mass star 2.0 solar masses plus 1.4, and both of them, they start at 32.5 kilometers. Wait, oops. this, okay. So this one is the SLY. Everyone can see the video, right?
Yes.
Okay. So this one is for AP4, and this one is for SLY, and the masses is 1.4 each. And you can, like, I'll start the movie, and then you can see that they do kind of a dance around each other, and you can see that a hypermassive neutron star is formed at towards the end of it. And if you do this one, which is the 2.2 and 1.4 solar masses, let me play the movie. This is done using two different software. That's why they look different. I had to use a different Python script because of the black hole, so over here, the merger remnant, it's not a neutron star. This is the example where it promptly collapses into a black hole and forms an accretion disk around it. So okay, let me play this again. You can see that the more massive star, it rips apart the less massive star, and it promptly collapses into a black hole, I think this is like it's really cool to watch the small star getting ripped apart by the really big
Make
stars.
sure the heavier mass star is actually the smaller one. It's the denser one.
Yes. The radius is small. Yeah, that's true. Okay. Back over here.
So, in the last clip, we saw the accretion. We saw matter flowing everywhere and then coming back to the accretion disk.
Yeah.
Does some matter get thrown away as well? Is there losses?
Yes, that does. Mass ejecta, it does get thrown away. So okay, wait. So this is where I'll be talking about future work. So one of the things that we want to analyze for the simulation is the mass ejecta. That is how much mass gets thrown away, like how much of the mass is bound and unbound, which is one of the analysis that we're going to do as part of our future work, and also what is the fate of the merger remnant. And we'll be performing higher resolution dynamical simulations of our initial data. So the reason why you need to do low resolution and then move on to high resolution is because these take really long time to finish, like on the time scale of weeks, and you need to submit it on supercomputers like either Frontera or Blue Waters. So now that we have data for low resolution runs, we can do higher resolution runs and get better physics out of it, which is part of my future work, and of course to graduate and write a paper. So thank you. I welcome questions.
Thank you.
Oh, I can.
Any questions?
Yes, I think that I missed the explanation of the simulation. The second one, what type of masses were merging together?
2 and 1.4 solar masses. So the gravitational mass of both the stars is 2 and 1.4.
But the objects are?
Sorry?
The objects themselves are what?
Neutron stars.
Neutron stars, okay.
Yeah.
Okay, I see, thanks.
In all cases, they're neutron stars, but in that one, in the end, 3.4 is above any expected mass limit for neutron stars, so it goes into a black hole.
It promptly collapses into a black hole.
Can you show the hypermassive one? The one that needs to be still rotating?
Oh, yes, this one. So this one, I didn't have. I don't know how long it would last for. I did not complete the entire simulation for it to actually collapse into a black hole, but it would eventually do that. I just need to run the simulation for longer and collect more data.
Collapse.
Did you run the simulation with initially spinning neutron stars?
No, they're not. Initially, they're not spinning. I use non-spinning configurations for this.
Why? Well, what would you expect to happen if you put them spinning?
I'm sorry, I'm not sure.
I'm not sure.
I think it is because LORENE has, like, we haven't been able to run configurations where the neutron stars are spinning using LORENE. So we are able to successfully run, produce initial data for non-spinning configurations using LORENE. That's the reason why we're using this.
Can you run in principle with LORENE with the spinning neutron stars?
I really don't know. I think we have to add more, like we have to add to the code for it to be able to do that. I don't know. I'm not sure. I'm sorry. I don't know about that. Even
Right.
like magnetic field also, we haven't tried that, putting magnetic field for the initial data.
Okay, thank you.
If you go back to the domains
Oh,
and sets and things, basically, is that where you put in that the system is in rigid motion, and I guess the domain sets don't
yes,
curl or twist and they don't cross each other? Is that
yes,
where?
yes, yeah. In the initial configuration.
Yeah, but the Einstein toolkit can run spinning black holes and spinning neutron stars, spinning components, right? It can follow more complicated things.
Yes, Einstein Toolkit can. I know they have done simulations for spinning black holes, but Einstein Toolkit can do it. But I don't think LORENE can. I'm sorry. I should. Yeah, I don't know about this.
I have a question.
Yeah. Yes. Please go ahead.
Once again, regarding the second simulation. So the formation of the black hole, like the moment that we have the first stage of a black hole inside the whole mess. So how deep in the ring down stage is this? Is that the first moment that we have the black hole?
For this one, yes, because we don't. So, like in the ring down, the merger remnant it forms, the merger remnant forms, right? And because there is no neutron star formation over here other than the initial neutron star, so it immediately collapses into a black hole.
So there is no ring down stage for this simulation?
The ring down, so it will, I feel like the ring down stage is where the black hole is formed and the accretion disk around it. So this is the ring down phase. It just wouldn't have a neutron star.
So, but okay, let's say this is the ring down process that I see now in front of me. So the black hole is already stable. The black hole itself, it's like formed and it just absorbs the matter around it.
Yes, it is formed and the accretion disk also forms around it, but it will eventually start accreting into the black hole, like,
okay,
because of the mass that is present.
So it will be some sort of mixed situation where I can see evidence for, like, no. My question is, will I see a ring down signal, like the typical ring down signal, combined with some electromagnetic signature?
I would believe so, that you would see a gravitational wave from the ring down phase, and also electromagnetic also along with it. I mean, okay, so I know this for sure for hypermassive, that we do see the gamma ray burst once the hypermassive star collapses into a black hole, and that's when the SGRB is seen by the different, like, Fermi saw that for GW 170817.
Okay.
Yeah, but I'm not very sure about for the prompt to collapse into a black hole, whether.
Yeah, I think it will be strange, no, to see a ring down pattern when this is a stable black hole. At least it's not forming to any other forming, just already a complete, like it should be.
Well,
right?
yeah,
Or maybe I'm missing something.
you can try to extract from numerical relativity simulation data first of all the horizon location at the moment when it forms, and then find the structure of the horizon surface and its multiples, and it can either be immediately identical to the multiples and position of a Kerr black hole, which is unlikely, or it would be some deviation from a Kerr black hole, in which case it would have to bring down to a Kerr black hole with emitting gravitational waves. So it would be more complicated in the potential because it's not just a vacuum all around it. You have all this, you have a lot of mass around it. But there is a place to look at these perturbations of the remnant black hole that's not originally perfect, and how it approaches an equilibrium, even if that equilibrium includes some mass accretion along through the disk.
So you're claiming that at the instance that there is some black hole, I don't care what is the size of it, it's not like well formed, it's not stable, it's yet stabilizing to I don't know, to the final product.
I don't know what you mean by stable, but it's not stationary, I guess. So it's not the final black hole. It will be a perturbed black hole.
Oh, okay. I mean, because you know, in the naive picture that we saw in the first slides of the merger of the ring down stage, you don't have like a formed black hole. You have some sort of black hole entity, right? Some combination of two black holes, and it emits radiation, gravitational. So,
Yes.
but here I see.
But over
here,
here,
but
this.
so we don't see here in the picture like a stable or I don't know, some well-formed black hole. But in the simulation, I see, at least with my eyes, like a perfect circle. So I'm trying to understand, is that perfect circle is
So
part
it's
of
an
the ring down
ellipse.
stage?
It's an ellipse, but because of the grid and the size of the grid, it looks like a circle. It's an
Okay.
ellipse. It's not a perfect circle.
So it should look like a ring down stage.
So the way I visualize the black hole is you can get where the apparent horizon is of the black hole, and then I try to fit an ellipse to it. And that's how, because right, you cannot, like, for the simulation, you cannot actually see inside of a black hole, like what's happening. So you just have to basically superimpose a black dot where you think the black hole is. So what I did was I fitted an ellipse to the where the apparent horizon. So I have the coordinates where the apparent horizon is, and I fit an ellipse to that. So
when you say an ellipse, you mean an ellipse in the plane of merger?
Yes, in the XY plane, yes.
Okay.
So that's basically just a dipole moment that you're taking as different from a circular black hole.
Yeah.
Should we expect higher moments as well?
Sorry?
Should we expect higher moments, different other deformations, or is an ellipse a good fit?
I guess an ellipse. So what some of them do is, like, one of the ways that they visualize the black hole is they just say the density inside the apparent horizon is less than the atmosphere, or you can fix it to atmosphere, and that's how you get the black dot in between. So the different techniques of getting the black hole to be there in the visualization. So I mean, at least when I tried to visualize the black hole just the way it is, it looked like an ellipse. It didn't look like perturbed or anything, but just for that particular simulation, at least.
Did you try to apply an actual horizon tracker?
Yeah. AH Finder in Einstein Toolkit.
Mm-hmm.
So yeah, it takes the apparent horizon at every time step that I wanted to, and then I fit an ellipse to that.
Mm-hmm. Any more questions? Okay, I have a question. I think it was on slide 12 with the domains.
Uh-huh.
So now these hemispheres for the two neutron stars and around them, is it because you're also assuming symmetry between up and down?
So they are not hemispheres, they are like spheres, because like it's an XYZ, all three directions. It's just to show if you do a cut how they would look.
So
See what
you
I'm
don't assume symmetry for between up and down with respect to the plane of the orbit?
Up and down with respect to the plane. I don't know. I don't know the answer to that. I guess no. I mean, at least I didn't read it anywhere. But yeah, I'll need to check it and get back to you with the answer to that.
Okay. Anything else? Anyone? We have a question in the chat. If it's an ellipse in the final ring down phase, shouldn't it keep producing gravitational waves?
Yes, it should. It should. It does. Ring down phase does emit weak gravitational waves.
So it emits gravitational waves and circularizes until it's not an ellipse anymore.
Yeah.
Any other questions? If not, let's thank the speaker once again.
Thank you. Thank you so much.
Thank you very much.
I've stopped